Today we're going to be doing May-June 2023 paper 52. Question number 1 says, 3 students are asked to prepare samples of benzoic acid C6H5COOH from the alkaline hydrolysis of methyl benzoate. Okay, it's an ester. If you hydrolyze the ester, you get a salt of the acid, which is sodium benzoate. Okay, that's the salt form. And then this is acidified with hydrochloric acid to form benzoic acid. So here you're hydrolyzing the ester. You're hydrolyzing the ester in alkaline solution. You get the salt of the acid and an alcohol. And then you take the salt of this acid, you react it with HCl, and you get benzoic acid. The student uses the following method. He first puts 1.242 grams of liquid methyl benzoate into a 50 cm³ round bottom flask, prepares 100 cm³ of 1 mole per dm³ aqueous sodium hydroxide. Okay, so I'm gonna highlight these values. We use 1.242 grams of methyl benzoate in a 50 cm³ round bottom flask. Then we prepare this solution, okay, 100 cm³ of 1 mole per dm³ sodium hydroxide. Then we add an excess of the sodium hydroxide to the round bottom flask. Add some anti-bumping granules to the round bottom flask. Fit a condenser to make a reflux apparatus. Reflux the reaction mixture for 20 minutes. Allow the reaction mixture to cool and carefully pour the liquid into a beaker. Acidify the liquid with dilute hydrochloric acid. Filter the mixture formed in step 7. Purify the benzoic acid by recrystallization from hot water. Filter, dry, and record the mass of pure benzoic acid obtained. So A part 1 says calculate the volume of the methyl benzoate used in step 1. Give your answer to the nearest 0.05 cm³. Okay, so we've been given the mass 1.242 grams and we've given the density, right? We know that density is mass over volume. We want to find the volume, so volume is just mass over density. The mass is 1.242 grams. Okay, 1.242 grams, that's given to us. And then the density is just 1.08, right? 1.08 grams per cm³. That will give us the volume in centimeter cube. So we get the volume as 1.15 centimeter cube, okay? 1.15 centimeter cube to the nearest 0.05 cm³. Identify a suitable piece of apparatus to measure the volume of methyl benzoate required in step 1. We want to measure 1.15 cm³ of methyl benzoate. We're going to use a burette, okay, to measure it. Calculate the mass of solid sodium hydroxide that is needed to prepare the solution in step 2. Now in step 2, we want to prepare 100 cm³ of 1 mole per dm³ aqueous sodium hydroxide, right? So here we've been given the concentration and the volume. So we can find the number of moles. Okay, the number of moles is concentration times the volume. Concentration is 1 mole per dm³. Volume is 100 cm³. Convert that to decimeter cube. We get the number of moles as 0.1 moles. And then we want to find the mass. The mass is just the number of moles times the molar mass, right? The number of moles here is 0.1. The MR of sodium hydroxide is 40. So we need 4.0 grams of sodium hydroxide. 4.0 grams of sodium hydroxide. Student 1 added the mass of sodium hydroxide calculated in A part 3 into a beaker. Describe the steps the student should take to make 100 cm³ of 1 mole per dm³ sodium hydroxide. Whenever we want to prepare a solution, we're going to use a volumetric flask, right? We're going to use a volumetric flask. Give the name and capacity of any apparatus that should be used. Write your answer using a series of numbered steps. Okay, so the first step, okay, we're going to number the steps. The first step is we're going to add a small amount of distilled water. Okay, add a small amount of distilled water, right, to the beaker, and dissolve the sodium hydroxide, okay, completely. The second step, okay, we're going to transfer this solution. We're going to transfer this solution transfer the solution to a volumetric flask, okay, to a 100 cm cube volumetric flask. We're going to rinse the beaker, okay. We're going to rinse the beaker 2 to 3 times with distilled water, okay, and transfer the washings. This is to ensure that none of the sodium hydroxide is left behind inside the beaker, right? So transfer the washings. And then lastly, we're going to make up to the mark, okay, make up to the mark, the 100 cm cube mark, okay, in the volumetric flask using distilled water, okay, using distilled water. And they don't usually ask for this, but at the end we always shake and invert, okay. We shake and invert the volumetric flask to mix the contents, okay, to mix the contents. Student 2 prepared 0.1 mole per dm cube aqueous sodium hydroxide instead of 1 mole per dm cube aqueous sodium hydroxide in step 2. State how this would affect the final mass of benzoic acid formed. Explain using calculations how you came to this conclusion. They've given us the MR of methyl benzoate and the MR of benzoic acid. Okay, so if you look at the reactions that are taking place here, right, these are the reactions that are taking place. I'm just going to take a copy of these reactions. Okay, look at these reactions over here. Okay, so these are the reactions that are taking place. Now over here, right, we were using 1.242 grams of the ester, 1.242 grams of the ester, and we were using 1 mole per dm cube sodium hydroxide, right? That was what the first student was using. Okay, that is what the first student was using, right? Now that means that the number of moles of ester is equal to the mass divided by the MR, right? The mass is 1.242, the MR is 136 for the ester, okay, and that gives us the number of moles as 0.00913 moles. Okay, so that's the number of moles of ester that we're using. Okay, that's the number of moles of ester that we're using. Now, what are we doing in this particular experiment? What we're doing is that in step 2 we prepare the sodium hydroxide, okay, and then in step 3 we add 10 cm cube of this 100 cm cube solution. We add 10 cm cube of this 100 cm cube solution of the prepared sodium hydroxide, right, to the round bottom flask. Okay, and then this sodium hydroxide is what reacts with the ester, right? This sodium hydroxide is what reacts with the ester. So what student 1 did, okay, student 1 used 10 cm cube of 1 mole per dm cube, used 1 mole per dm cube sodium hydroxide, right? Used 1 mole per dm cube sodium hydroxide. So initially, right, what we had was initially the number of moles of sodium hydroxide, right, number of moles of sodium hydroxide in the first case, okay, in the first case, so I'm going to write student 1, number of moles of sodium hydroxide was concentration times volume. The concentration was 1 mole per dm cube and the volume we were using was 10 cm cube, right? So initially the student was using 0.01 moles, right, 0.01 moles. That was student 1, okay, that was student 1. But student 2, instead of using 1 mole per dm cube, is using 0.1 mole per dm cube sodium hydroxide, okay. Instead of using 1 mole per dm cube sodium hydroxide, he is using 0.1 mole per dm cube sodium hydroxide. So now, in the case of student 2, right, the number of moles of sodium hydroxide is again concentration times volume, but the concentration is now 0.1. We're still using 10 cm cube, so that's 10 over 1000. So that's 0.001 moles. Now, if you notice, the ester and the sodium hydroxide are reacting in a 1-to-1 ratio, right? They're reacting in a 1-to-1 ratio. Initially, the sodium hydroxide was in excess. When student 1 used 1 mole per dm cube sodium hydroxide, we have more moles of sodium hydroxide than we do of the ester, right? But in the case of student 2, right, student 2, sodium hydroxide is no longer in excess because he is not using 1 mole per dm cube sodium hydroxide. Now, since the sodium hydroxide is no longer in excess, it means that not all the ester will react, which will obviously result in a lower mass of benzoic acid being made, right? So in the first case, sodium hydroxide was in excess, right? But in the second case, sodium hydroxide is not in excess, right? Not in excess. Since it's no longer in excess, we're going to have a lower mass of the salt being produced, okay, and then we're going to have a lower mass of the benzoic acid being produced, right? We're going to have a lower mass of the salt being produced and therefore a lower mass of the benzoic acid being produced. The effect on the mass would be that the mass of benzoic acid produced would decrease, okay, or a lower mass, okay, a lower mass would be produced, okay. Mass decreases, okay, and the reason why is because the sodium hydroxide, okay, is no longer in excess, okay, is no longer in excess, okay. Okay, therefore not all the ester reacts, okay, not all the ester reacts. D part 1 says explain why it is necessary to reflux the mixture in step 5. And when we say reflux, okay, we mean that why is it necessary to heat the mixture under reflux, right? Why is it necessary to heat the mixture under reflux? Now, the purpose of a reflux condenser, right? The purpose of a reflux condenser is that it basically allows us to heat the contents of the flask, okay? It allows us to heat the contents of the flask without the contents of the flask escaping, right? Without the contents of the flask escaping. So here I've shown a small diagram, right, for how a reflux condenser works like this, right? So this is our reflux condenser, okay, reflux condenser, right? And what happens here is that when we heat the contents of the flask, when we heat the contents of the flask, right, the contents of the flask can escape. The contents of the flask can escape, okay? So we need to use a reflux condenser. When we use a reflux condenser, right, as those substances are evaporating or boiling, right, they're going to condense back down into the flask. Okay, they're going to condense back down into the flask. We can't seal the contents of the flask. We can't seal the contents of the flask because that would lead to a pressure buildup, which would be dangerous, right? That would lead to a pressure buildup, and that would be dangerous. Okay. The reason we heat the contents of the flask is to increase the rate of the reaction, right? We want to increase the rate of the reaction, right? That's where we're heating. Increase the rate of the reaction. But we also want to ensure that the contents of the flask do not escape, right? Ensure that the volatile contents, okay, that the volatile contents of the flask do not escape, okay? Okay, that could be the reactants or the products, okay? Explain why a naked flame is not used in step 5. The reason we don't use a naked flame is because we have flammable substances, okay? So flammable substances, okay, are being heated, right? Explain the purpose of transferring the liquid in step 6. Now, what are we doing in step 6? In step 6, we're allowing the reaction mixture to cool and carefully pouring the liquid into a beaker, okay? The reason we're carefully transferring the liquid, okay, is because inside the round bottom flask, right, we were using anti-bumping granules. Right? And we don't want the anti-bumping granules, so we're going to carefully transfer the liquid from the round bottom flask into a beaker. Okay, the reason we use anti-bumping granules is to ensure uniform heating. Okay, anti-bumping granules are used to ensure uniform heating and also to ensure that we don't have very large bubbles being produced, okay, which could result in uh, liquid spilling over or liquid sort of boiling over, and that would be dangerous. Okay, so we want to ensure uniform heating and we want to make sure that we don't have large bubbles. That's why we use anti-bumping granules. And then the reason we transfer this liquid to a beaker, okay, is to remove the anti-bumping granules. Okay, so done to remove the anti-bumping granules. Okay, so the anti-bumping granules stay behind. Okay, they stay behind in the round bottomed flask. Okay. Explain what the student should do to confirm that the mixture has been acidified in step 7. So to check that the mixture is acidic, okay, we can use an indicator. Okay. So we can use an indicator, okay, like methyl orange. Okay, so what we're going to do is we can add a few drops. Okay, we can add a few drops of methyl orange. Okay, add a few drops of methyl orange. Okay, and methyl orange should turn pink. Okay, the solution or the mixture should turn pink. Okay. Another thing we can use is we can use a pH probe, right? We can use a pH probe or a pH meter to monitor the pH in the mixture. Okay. Describe what you would expect to observe as the sodium benzoate mixture is acidified in step 7. Now, if we go back, right, in step 7, what we're doing is we're adding the HCl, right, to the mixture. So we had this reaction take place. We formed the salt of benzoic acid, right, sodium benzoate. And when the sodium benzoate reacts with HCl, we get solid benzoic acid, right? So when you acidify the liquid with dilute hydrochloric acid, okay, what you're going to see is you're going to see the formation of solid benzoic acid. So the observation here will be that the solid benzoic acid will form, okay? Or we can say that a precipitate will form, okay? Precipitate forms. Suggest why it's necessary to cool the mixture before filtering in step 9. Now in step 9, right, in step 9 what we're doing is, in step 9 we're basically separating, okay, we're separating the solid benzoic acid from the mixture, right? We're separating the solid benzoic acid from the mixture by filtration, okay? By filtration. The reason we want to allow the mixture to cool is so that more precipitate forms, right? If the mixture is hot, a lot of the benzoic acid may remain dissolved, okay? It may remain dissolved in solution, okay? We want to ensure that we obtain the maximum possible mass that we can of benzoic acid, okay? To do that, we're going to allow the solution or the mixture to cool. If we allow it to cool, okay, we're going to get a greater mass of precipitate forming. Less of the benzoic acid will remain dissolved, okay? Less of the benzoic acid will remain dissolved. The reason we allow it to cool, okay, the reason we allow it to cool is because the benzoic acid, okay, benzoic acid is less soluble, okay, less soluble in cold water, okay. So allowing it to cool ensures, okay, therefore this will ensure, okay, ensures that we're going to obtain a greater mass, ensures a greater mass is obtained. Pure benzoic acid has a melting point of 122 degrees Celsius. The product made by student 1 has a melting point of 119 degrees Celsius. The student suggests the melting point of the product was lower than expected because it contained some water. Explain what the student should do to ensure that the product no longer contains water. Now to ensure that there's no water left, okay, what we're going to do is we're going to heat it. We're going to heat it to drive off the water and weigh the contents, right? I'm going to keep doing that until the mass remains constant, right? I'm going to keep doing that until the mass remains constant. So what we can do here is we can dry the benzoic acid in an oven, right? Dry in an oven, okay, and then weigh, okay, and then weigh the sample, okay, and then we're going to repeat, okay, we're going to repeat until constant mass is obtained, okay, until constant mass is obtained. Calculate the maximum mass of benzoic acid that can be formed from 1.242 grams of methyl benzoate. Okay, so again, we know the number of moles of the ester, right, was 0.00913 moles. So the maximum number of moles of acid, so the maximum number of moles of acid that we would obtain is the same, right? Assuming we have 100% yield, okay, assuming we have 100% yield, right? there's a 1-to-1 ratio between the ester and the acid. So 1 mole of ester would give you 1 mole of acid, right? That would be the maximum yield, the maximum number of moles, which means that the maximum mass would be the number of moles times the MR for the acid. So that's 0.00913 times 122, right? That's the MR of the acid. And that would give us a maximum mass of 1.11 grams. Okay. The maximum mass of benzoic acid is 1.11 grams. Student 3 produces 0.825 grams of benzoic acid from 1.242 grams of methyl benzoate. Calculate the percentage yield of benzoic acid produced by student 3. So this would just be 0.825, right? That's the actual mass obtained. Divide by the maximum or the theoretical mass, that's 1.11, okay, times 100. Okay, so this is the actual divided by the theoretical or maximum times 100. And so we get the percentage yield as 74.0%, okay, 74.0%. So here we have question number 2, which says pure water dissociates according to the following equation. The equilibrium constant for this reaction is known as Kw, the ionic product of water. At 25 degrees Celsius, Kw has a value of 1 into 10 to the power minus 14 moles squared per dm to the power 6 or dm to the power minus 6. The pH of pure water at 25 degrees Celsius is 7. A student finds the pH of pure water at 35 degrees Celsius is 6.84. The student investigates how temperature affects the pH of pure water and determines a value for the enthalpy change for the dissociation of water. The student records the pH of pure water at different temperatures. A line of best fit from the results of the student's investigation is shown in figure 2.1. Okay. Now over here, the first thing we're going to do is we're going to outline the objective, right? The objective is to determine the enthalpy change for the dissociation, right? For the dissociation of water. So that's what we're trying to determine. They've also told us that the student determines that the pH of pure water decreases, okay, pH decreases at a higher temperature. A lower pH means that at a higher temperature, right, at a higher temperature, the amount of H plus in solution increases, right? The amount of H plus in solution increases. Higher concentration of H plus would mean lower pH. Higher concentration of H plus would mean lower pH. So that means that increasing the temperature shifts the equilibrium to the right. So we know that this dissociation must be endothermic. Okay, we know that this dissociation must be endothermic. Okay, they've given us the graph. They've given us the graph of the pH of pure water against the temperature. And again, as temperature increases, the pH is decreasing. Okay, in other words, the concentration of H plus and OH minus is increasing. The equilibrium is shifting to the right, resulting in a higher concentration of H plus and therefore a lower pH. Right. So that means the reaction must be endothermic. Use figure 2.1 to calculate the hydrogen ion concentration of pure water at 45 degrees Celsius. So if we go to the graph, right, at 45 degrees Celsius, so this is 45 degrees Celsius right here, right, the pH is 6.7, okay, the pH is 6.7, so this, right, so we get a pH of 6.7, we have to find the concentration of H plus. You should know that the concentration of H plus is 10 to the power of minus pH. So that means that the concentration of H plus is 10 to the power of minus 6.7, 1.995 into 10 to the power of minus 7 moles per dm, right? Which is just 2.00, okay, 2.00 into 10 to the power of minus 7 moles per dm cube. Calculate the value of Kw for pure water at 45 degrees Celsius. Kw is the concentration of H plus times the concentration of OH minus. For pure water, these two are the same. Okay, for pure water, these two are the same. H plus is equal to OH minus, right? H plus is equal to OH minus because water is neutral. And so we can say 1.995 into 10 to the power of minus 7 squared, right? And that gives us the value of Kw as 3.98 into 10 to the power of minus 14. Okay, 3.98 into 10 to the power of minus 14. State the relationship between Kw and temperature. Well, we can clearly see that Kw is increasing Okay, Kw is increasing as temperature increases, right? At 25 degrees Celsius, 1 into 10 to the power minus 14. At 45 degrees Celsius, almost 4 times bigger, right? So we can say that Kw increases, it increases as temperature increases. The student determines Kw at a range of temperatures. The results are shown in table 2.1. We want to complete table 2.1. We want to record 1 over T to 3 significant figures using standard form. Okay, so that's what I've done here. I record in standard form to 3 significant figures. We want to record log of Kw, okay, log of Kw to 2 decimal places. Okay, the temperatures are given to us. We can just find 1 over T, write it down in standard form to 3 significant figures, and we can also take the log of Kw, right, and write it down to 2 decimal places. Okay, pretty straightforward. Okay, but please make sure that you guys don't make any silly mistakes rounding these values. Okay, because if you make a rounding error for even one of these values, okay, you're going to lose the mark for the entire column. Okay, you're going to lose the mark for the entire column. So please make sure that you guys don't make any silly mistakes when you're rounding. Okay, round correctly. Plot a graph on the grid to show the relationship between log of Kw and 1 over T. Use a cross to plot each data point and draw a line of best fit. Okay, so I've done that here. Okay, I've drawn the line of best fit right here. Okay, so this is my line of best fit. Okay, I've also circled the anomalous point. I've circled the anomalous point here as well. Okay, and I've shown the 2 points. I've shown the 2 points that I've chosen to find my gradient. Okay, so the way to draw a line of best fit is to ensure that the points above and below the line are roughly canceling each other out. Here, all the points almost perfectly lie on the line. Okay, so these are relatively good data points. They're relatively good data points, but if you had data points that weren't as nice, okay, you just want to make sure that the points below the line and above the line cancel each other out. Okay, and I would always draw construction lines. Okay, I would draw construction lines to show the points that I've chosen to find the slope. Okay, now the points that you choose to find the slope should be at least 50% of the graph distance apart. In other words, try to choose 2 different points for the slope that are as far apart as possible. Okay, try choosing points, okay, that are as far apart as possible when you want to calculate the slope. Okay, so don't choose 2 points that are very close to each other, okay, when you're calculating the slope, okay, or for the calculation of the slope. Okay, so I've plot the graph. Okay, I plot the graph, drawn the line of best fit. I've circled the point that's anomalous, right? Part 4 says, suggest one reason to explain the anomalous point you have circled. Assume there was no error in determining Kw. So the question says that there was no error in determining Kw. Okay, there was no error in determining Kw, right? So here we have the anomalous point, right? We don't include the anomalous point in our line of best fit, okay? And we're saying that there was no mistake made when we were determining Kw. There was no mistake made when we were determining Kw. That means that there was a mistake made when we were recording the temperature. Now at this particular value, okay, at this particular value of 1 over T, at this particular value of 1 over T, Kw should be higher, right? So for this particular temperature, right, they're saying you've calculated Kw correctly. So there's some mistake that we made in recording the temperature, right? Some mistake that we made in recording the temperature, because this point should be somewhere here, right? For this particular temperature, the point should be higher. It should be somewhere here on the line, right? So the Kw value that you determined should have been higher, right? So the Kw value that you determined should have been higher. So we can say that for this particular point, right, Kw should be higher. Okay, Kw should be higher, right? So this calculated value of Kw, this calculated value of Kw is lower than it should be. The calculated value of Kw is lower than it should be, and we know that as the temperature increases, Kw increases. So if this value is lower, that means that the temperature is lower. Now this value, right, this anomalous point is at negative 12.84, right? This anomalous point is a negative 12.84. Okay, so this anomalous point is a negative 12.84, right? That's the log of Kw, right? And that was for a temperature of 343 Kelvin, right? That was for a temperature of 343 Kelvin. However, we're saying that this value for log of kW, and therefore kW should be greater. Okay, this value of log of kW, and therefore kW should be greater at this particular temperature. It should be greater at this particular temperature. That means that the actual temperature was lower than this. The actual temperature must have been lower than this because we got a lower value of kW. The actual temperature was lower because we got a lower value of kW. Okay, so over here we can say that the pH, okay, the pH was recorded, okay, at a temperature lower than, okay, at a temperature lower than 343 Kelvin, okay, lower than 343 Kelvin, okay. In other words, the actual temperature was lower, okay, than the recorded temperature, okay, than the recorded temperature. Okay, and that resulted in a lower value of kW. The value of kW for that particular temperature should be higher. Use your graph to determine the gradient of the line of best fit. State the coordinates of both points you used in your calculation. These must be selected from your line of best fit. Okay, we can't use the plotted points. And again, the points that you choose should be as far away from each other as possible. Okay, now the gradient is the change in y over the change in x, right? That's y2 minus y1 over x2 minus x1 plus minus 14.58 minus 12.52 divided by 0.00355, that's 3.55 and 10 to the power minus 3 minus 0.00285. Okay, and that gives the gradient as negative 2943. So the gradient is minus 2943. The relationship between log of kW and 1 over T is given by the equation shown. Log of kW is equal to minus delta H divided by 2.303 RT plus a constant. Use the gradient determined in B part 5 to calculate a value for the enthalpy change in kilojoules per mole for the dissociation of water. If you were unable to determine a value for the gradient, use the value minus 2550. This is not the correct value. Now the value for the gradient that we got was minus 2943, right? Now if you look at this equation, right? If you look at this equation right here, right? The graph that we've drawn, okay, the graph that we've drawn is log of kW on the y-axis, right? And we have 1 over t on the x-axis, right? So we have minus delta H over 2.303 R, right, times 1 over t plus some constant, right? Plus some constant. So we have the graph in the form y, okay, y is equal to m, okay, this is m, okay, and then 1 over t is on the x-axis and then plus c, right? So we have a straight line, right? Y is equal to mx plus c. The gradient that we've determined is this minus delta H over 2.303 R, okay, minus delta H over 2.303 R, where R is the molar gas constant, okay. So again, we have log of kW on the y-axis and 1 over t on the x-axis, okay. You want to separate that 1 over t from this expression. You want to separate that 1 over t from this expression, right? So we have minus delta H over 2.303 R, that's the gradient m, times x, okay, that's 1 over t, plus a constant c, right? That's the y-intercept. So we can say that our gradient minus 2943 is equal to minus delta H over 2.303 R, okay, and R is just 8.31 joules per mole per Kelvin, okay. So that gives us the value of delta H as 56,323 joules per mole, okay. Be careful about the units, okay, they want the answer in kilojoules per mole, but the molar gas constant, that's 8.31, is given in joules per mole per Kelvin, right? Again, you can refer to the table at the back of the paper, right? The molar gas constant given in joules per Kelvin per mole, okay. So we've determined the enthalpy change in joules per mole, and we can just divide by 1000, and that gives us the enthalpy change as 56.3 kilojoules per mole.